So now let us do the maximum term method. As I saying here that this is, one can show that the maximum term method is bounded and a very rigorous bound. The bound is, that means there is this quantity Pn which is very small, one can show that maximum term method, and the remainder remainder goes to 0. So now I want to replace the partition function by logarithmic term. So what I am going to do now, I am going to take that ml star. So I am not going to do this sum now, I am going to replace that by 1 ml star. That ml star, that particular distribution which maximizes these things. So I do not have the sum anymore. So this is the quantity I have to maximize, right? Clear? So now we do that. So this is the maximum term method. So I take, this is the mistake I said. I do not know how these mistakes come, this should not be there anymore, because we are just maximizing ml star. So now I take the log of that. When I take the log of that, now I have to have with the constraint that LML equal to n. So log of that, you can have all these term ml star minus LMN, LL, L, ML, LL, ML, sum over ML is n. So this quantity is here, and this is then VBL to the power ML, all these things. You can check it and you will find that. Apply now maximum term method with the constraint, that is why that extra n will become, and then you get this quantity. It used to be Z with the bracket LML minus n, n does go out, LML remain, and then I put it as a lnz, my Lagrangian multiplier. I take the notation lnz knowing that what will come later, and then I take with respect to ml, and that would, this ml, LML, remember that is a constraint, that have to be n, that is why it is there. And then you get this quantity from here, ln ml lnz, then you, as I said, I put it by hand as a Lagrangian multiplier lnz, ml star VBL to the power ZL. These come from there, everywhere it should have been ml star actually. Like it should be star here, it should be star here, it should be star here. I can try to do that with certain luck, and KBT should be lowercase. These all should be star, ml star. So this is right here, but everywhere it will be ml star. The ml star is that. So now you understand the details, and you also understand the grand picture. So n, so once I get that, I multiply it. I know that must satisfy n. I do that, hit by L and do it, then I get n, I get sum over V, L, BL, Z to the power L, then I get density equal to L, BL, Z to the power L. This is a very important equation, correct? Right? So this is this, alright. Okay, now I have partition function like that, I take log of that, then I can now calculate the free energy in terms of my ml star. I know my ml star is this quantity here, right? I know my ml star. Now partition function does not have the sum, this is correct. Then I can calculate the free energy by ml star coming out, the ln of that, VBL, and this term, believe me, this is all this term is here. And then I can get the pressure by taking derivative of that. Are you following the thread or you are losing? Okay. Then right now, if you go into the very detail of the equations, you will get lost. This you can check it up, and it will take me probably half an hour more to do that. So, I do not want to do that, and it is probably, since these are details of a keeping at that level of probably these are not details, you can do it because it will take you 10 minutes to do it, but you can do it. So, that goes inside, and when I do that, there are these two terms here, ln z and ln z will go to 0 ddv, but I have this term left, vbl term left. So, I take ddv there vbl. So, then I get pressure doing that is kbt bl0. So, pressure K should be lower case, P by kbt is this second quantity. So, these two together are called the cluster integrals, the cluster expansion, sorry. So, when you call a mere cluster expansion, usually this is the thing. It's really a matter of a choice. And these are exact. One can do probably somewhat simpler way through the grand canonical ensemble, but there are some results what you won't get from there. Okay. So, this now, as I was saying, the game plan now is to eliminate viscous fugacity from these expansions. Both are exact, believe me that. Elimination of fugacity from here gives you another infinite series. That infinite series is the following. And this is a Virial series. That is one of the things you taught in your high school also. The pressure is the expanded density, first term is the second Virial coefficient, which will show is exactly given by F2 term of Mayer cluster expansion. F2 term is an integral over interaction, interatomic potential, intermolecular potential. So, now from the historically from B2, the interaction potential, the first force field was derived from B2 because it was done after Mayer did. One finds that second Virial, I can get the second Virial coefficient how? I plot pressure versus density, and this is the ideal gas. But if as interactions become important, I see this starts deviating. So, I know experimentally this quantity, and I know the first part of deviating is very temperature dependent. Like high temperature it is like this, low temperature it is like that. So, from there I fitting, I get the temperature dependence of second Virial coefficient, and I will now show you the second Virial coefficient is the integral over the first irreducible cluster integral or B2. Okay, second Virial coefficient. Okay. So, now, so I am going a little bit back and forth to give you the understanding of what is going on. Okay. This will not need immediately, but very important. So, what Mayer did then, these B's that we have done are called reducible cluster integrals. These are with the definition given here. These are integrals. However, as we know that this cannot be reduced any further, but this can be reduced. So, now we think, is it possible for me to express BL following the same logic that I can now say, okay, I have a cluster whose weight I have given as BL. That weight now, that particles now, I can now define this quantity as 1. It is constructed of 2 bonds, if of them are same bond, but this is a different thing. So, can I further decompose these group of clusters into this quantity and this quantity, given that this is irreducible? And that was the next thing that Mayer did, reduction in terms of irreducible cluster integral. Now he said, okay, let me define these are the fundamental quantities. These as this I cannot reduce any further, this and these are the quantities. This actually should have one more, because it should have the one without a bond, okay, that somehow is not given here. So this one now I define, this is not kappa, this is k, beta k, this volume, this quantity, exactly define the similar way as we did before. We can do the exactly same thing, that I now want to distribute in my ml or nl, how many of them are this kind and how many are of that kind. So we do the exactly same analysis we did before, and you get slightly different expression, but you can show that it goes over the further decomposition, and this however has an approximation. In the process of going this approximation, that you have to assume that these are volume independent, only then this reduction can be done, and that turned out to be very important limitation in this theory, which made the theory more questionable at high density. Okay. So, I will not spend too much time on this. If I want to do it, I will do it later, but right now I am going to do something else. That so this is the irreducible cluster integral. So now my aim is to show this quantity is the second virial coefficient, this quantity is the third virial coefficient, and sum of all these things are the fourth virial coefficient. And as I told you, these are important historically and also for force field development even today. So with time, priorities have changed. There is that huge amount of effort at one time went to get these integrals, really huge amount of work went, and that succeeded to some extent, but not to a great extent. So basic idea is that this is the thing, and then there is a reduction. You can, there is a distinction you should know. Beta 1 is 2 particle. So beta 1 is first of the irreducible integral. That is good, gives on to B2. So B3 is the 3 particle clusters. So this has 2 of these, but there is one stands out, which is beta 2. So when I think of B3, I have B3 is decomposed. That's how it was done. The way I always do, or you can always do, you can always, I never do it this way. I always write down 2 particle, then I do the 3 particle, then I go to 4 particle, then I see the pattern. That's how Mayer did it. BS. That doesn't come from there. That comes from these definitions. So there is the 3 part of A will come, 3 of them, I think 3 factorial, 3 will, they are all the same value. 3 factorial cancels the 3, I think you are left with 2. That's work it out. But as far as I remember, 1 over 3 factorial into 3, and then you left with 2. And here, however, nothing is there, so the 3 comes in, because the 3 of them are not there. That's why you get a 3 factorial here. But let me say something very interesting. So this part was done by Mayer. Now Mayer had a very smart wife. You might be knowing, called Goppert Mayer, Maria Goppert Mayer. So they were in Göttingen, and Maria Goppert Mayer was the daughter of a professor. She was very beautiful, and very smart. So, there are all those people who are there, George Gamow and all the people, Mayer, they gone to Göttingen to study. So, finally, Joseph Mayer managed to convince her and marry her, and they brought her to they are first in job in Columbia. Those days women's faculty position was very difficult. So, Maria Goppert Mayer didn't get a faculty position. She was just, I don't think she was probably not even paid, but she was incredibly smart. So, while Mayer did the first part, this part was done by Maria Goppert Mayer, and that is acknowledged in Mayer. So, they wrote a book of StatMech, which is Mayer and Mayer, very famous statistical mechanics books. Much of the things are taken from that book. Also, the Patria, R.K. Patria has a good job, and my book also, I hope the equations are all correct. That was done by Maria Goppert Mayer. Then another interesting thing happened. Sometime later, there is a PhD student of Mayer called Stockmayer, who was very famous. Stockmayer did the theory of sol-gel transition, when the polymers get together and form a gel. There is a difficult combinatorics of this kind, and that was also done by Goppert Mayer, and Stockmayer wrote the paper and acknowledged the contribution of Goppert Mayer in that theory. And in Chicago, then they came. Even then, Goppert Mayer didn't have any office. So, in the first floor or ground floor, American first floor or ground floor, in James Franck Institute, I think she probably had in the Enrico Fermi part, which is demolished all these things now, except where the Fermi did the nuclear chain reaction, that part is on the cap, and the capsule is there. There is a long hallway, and in the hallway on side they put a desk and a chair, and Maria Goppert Mayer used to sit on the hallway. And when so Fermi, so people know he was Mayer's wife. So, once Fermi was going there, and Maria Goppert Mayer was doing some calculations. So, Fermi stopped and asked, what is she doing? He said, oh, I am trying to develop a theory of nuclear shell theory. Fermi said, that is very interesting, I was thinking about it. You know, it should be something like Bohr's theory, you know, the same kind of thing. And that gave Maria Goppert Mayer presumably the basic idea, which went on to do in the famous theory of nuclear shell, which they got the Nobel Prize ultimately. So, there are all these stories which are hangs around in famous places like this James Franck Institute or Enrico Fermi University of Chicago or everywhere else. For example, like when you go to Harvard, you hear the chemistry department, lot of beautiful stories about Bob Woodward, who is one of the father of organic chemistry, but whatever. So, now let me go back and forth little bit. Now, so these are the integrals, the same as with a factor of 2, same as the second of reducible cluster integrals. There is the first of reducible integral, there is this difference of 1 between them, but this is the integral, you have to remember. So, it is f12, and remember f12 is Mayer F function. So, f12 is this quantity e to the power minus beta u12 r minus 1. So, then beta 1 dr right, and then that is dr 4 pi r square beta ur minus 1. Okay. So, there is a factor of volume in front. So, this is a strongly temperature dependence that comes from beta, 4 pi comes out 0 to infinity 1 pi 4 pi v, right, yeah 4 pi v. So, This is the expression of my first irreducible cluster integral, which is also V2 by 2. Now I will show you how that happens, and we will stop after that. Before that, one tiny little bit, that one can go and calculate the average number of these clusters by using this. There is a, what turned out is very powerful, that this exact partition function is nothing but a class of polynomials called Bell polynomials, a very powerful polynomials used, the famous mathematician Bell, that has been used in many ways, particularly in study of zeros of polynomials. That polynomial allows you to write a recursion relation. It is just a bit of good luck. Now, if I can write this, then if you can give me the Z1 and then give me next one, I can get the higher level partition function. So, I can construct this called recursion relation. The input of course are the BL plus 1. So, if I have that, I can construct this partition function. If I can construct the partition function, I can calculate what is the average number of clusters in the particle by using these as the weight, So, this is the weight of a one particular distribution, right. If I have the partition function, then I calculate that weight. I am not going to go to the details of that, but then you can now say, okay, LML is the number of clusters, LML is number of particles in size of cluster L. ML is the number of clusters of size L, each of them have L. So, LML is the number of particles in cluster of size L. Now, we plot it against L by N is the total number of particles, L is the size of the cluster. Then you find when you have high temperature, then this gas goes to be 0. But when you lower the temperature, you find a second peak appears. That second peak is the liquid. So, a second big cluster appears with L by N close to 1, slightly less than 1, maybe at 0.8. So, as you hit the coexistence, this peak signals the appearance of a macroscopic cluster in the system. So, liquid is envisaged in Mayer's theory as a macroscopic cluster. Okay. So, when you cool down, like nitrogen we have, I cool it down and make the density large, then the particles come close to each other, they all start interacting. I call a system a liquid when all the particles are interacting with each other, or one of them is interacting many others. But if one is interacting with say 10, which is a good number actually, then it's correct, almost correct number, then the neighbors of that, my 10 neighbors, they are interacting with another 10, then another 10. So, liquid means when the particles are all talking with each other, or molecules are talking with each other. That means in this description they are part of the same cluster. They are talking with each other means they are connected by a bond. This is not a chemical bond, the bonds are breaking and forming, but they are interacting. So, liquid is that not each particle need not interact with everybody. Okay. So, this is the, again I repeat, ML is number of particles in cluster of size L. LML is ML is number of clusters of size L. LML is number of particles in that cluster. Okay. And then this is L equal to small 1 or so, 1 by N equal to very small, that are the gas, the small clusters. When they are large, this goes close to when L is close to N, that means a gigantic macroscopic clusters, this is close to 1, maybe 0.8 or so. So, low temperature this peak appears. high temperature there is no peak. Huh? This is the low temperature. The high temperature I should have just like this. So that should have been there and it is not there. So this is a nice physical picture that comes. As I told you, ideal gas doesn't form liquid. Liquid forms because of interactions, and that interaction lowest level is the second or third virial coefficients. That is not perfect theory by any means. This theory to take you all essentially to a picture and how interactions are taken into account, but that is the universal scheme. All other theories flew from that. So if I take now L ml and then L by N, then as she asked, in the high temperature gas phase, this is just like this. I lower the temperature, increase the density, it becomes like that. Then finally, that appears. This is one. Okay. So this is the pure gas, no liquid. Large clusters are appearing. Then at the coexistence, you have lots of gas and then also one gigantic cluster. So if I plot this thing as pressure versus density, then this is like that, which is here, then it becomes more like that, which is this one, and then it becomes. So this one is this one, gas and liquid are together. This is the coexistence. So you have one gigantic cluster, which is the liquid. It's amazing when your liquid is in an equilibrium with a vapor phase, just like in glass of water. Then in the liquid, you have this Avogadro number of particles interacting with each other. But your liquid, your gas is just cluster of 2 or 3. This is a huge separation. And one is stabilized by entropy, which is your gas. One is largely stabilized by your enthalpy, which is this phase. And this really took huge amount of time for people to describe this phase transition. Huge amount of money. I always consider phase transition is where almost all our concepts came, including high energy physics. Because that's where came the order parameter, that's where came the interactions among atoms and molecules. So phase transition is the one everybody should study. The free energy diagram and all these things, even our chemical kinetics is deeply aped, though independently it was developed in the beginning. Now, one little bit, because I don't know when we will meet first, one little bit the virial expansion from Mayer's theory. So then I go to the partition function and I say, okay, I expand this expansion and I start putting my v's together. I take only this term. Then we know n into n minus 1, 2 of them. I will do rest of the integrals. I did v to the power n minus 2. Correct? There are only 2 I cannot do, which 2 are kept here. They are vector integrals. Then I change the center of mass to what? One volume comes out. This is my Mayer function. Actually, it should be u. However, now I take this v out, it becomes v n minus 1. Large n limit, I can neglect this. I have n square by 2. And then I bring it here, take Vn out, 1 by V comes here, it becomes 1, n square beta 1 by V. beta 1 as a volume term, okay, and in general, so this you can, this is the partition function. Now I take this tiny little bit of partition function, only this part, tiny little bit. I just looking at a correction. That correction, so I am interested in this part. I am interested in this part or this part. I am not doing this one, but I am doing a tiny little part to make it simple. A full derivation can be done, that will be a little complex, so I am not doing it. So now I am going to do that, put that back in my partition function. This Zn, I put it back in my free energy, this definition. Then I log, this is a large volume and NV, and then I take this derivative, and then this becomes 1 over V, that becomes 1 here, and that derivative gives this is suddenly developed, but at the end of the day this is n by V by n, so PV by n kBT, you get exactly from here, you get exactly this term. So this is the first of an expansion. So PV by n kBT is this Virial series. So now I identify B2, second Virial coefficient is minus beta 1 by 2, this quantity from minus beta 1 by 2, and this is then my microscopic expression of the second Virial coefficient, except this is not VR, is U. So I think Homework has used his notes and screwed up everything very nicely, but this is what it stands now. This is a beautiful expression. Second Virial coefficient, which describes this bending here, is in terms of Mayer cluster integral, and this is the general expression one can derive. And one little bit I can go to Van der Waals equation, I can find out my Virial coefficients. This is a homework problem we always give. You expand it, pressure in terms of density, and equate this thing, you get the second Virial coefficient, third Virial coefficient. Go back, find out the betas, then find out betas, these are betas, find out your Mayer cluster integral, which can be done by use a very similar recursion relation. So you can construct whole statistical mechanics that lies under Van der Waals, and that has been done. So we stop here today. There are some limitations. One of the major limitation is that when one goes to that level, this is only temperature dependent. In doing these integrals, the way defined only when volume dependence of those integrals are neglected, and that is the, so this is the, it does not describe, because it diverges there, and it does not describe the liquid state. So Mayer's theory does not work in the liquids, but it describes how liquid forms, it describes how singularity develops, and it describes how which singularities are the affair. So what we will do now, after this we will do Landau theory, which is the theory of phase tensor. I am hurrying a little bit. Any questions you quickly ask? Yes. That's a very series. Yeah. Quantitative change. This part is quantitatively exact. It is just making it more accurate. Correct. You don't see anything fundamentally different. No, say for example, when you go to liquids, then something fundamentally different appears here. For that you need infinite number of them, and that part where it breaks down. But it, as I said here, it reproduces the complete flattening. It reproduces this part. But then it does not, because for that, people have done little better and corrected this theory, but people are quite happy with this part, that it, starting from an interaction potential to see how a temperature dependent behavior emerging was really quite satisfying. And the concept of clusters, we went on to good percolation. This is the way after that percolation theory was done, sol-gel transition done. So this played as a catalyst of development of hell lot of things. That's why historically in statistical mechanics these things should not be ignored, Mayer's theory. People don't teach it because it's too complex, as you have seen. And it so next we will do on phase transition, I will explain little bit more. Okay, I think we stop here today.